Today we are doing volumes of solids of revolution, disks, and washers. And for a given base, you create semicircular cross sections sticking toward you and sticking away from you. You have created circular cross sections. Since the volume of the area of a circle is pi r squared, the formula for the volume with circular cross sections is pi r squared dx, or don't forget that pi is a constant, so we can stick that out front, and we can also be rotating it or being perpendicular to the y-axis, so we need to keep this in mind of whether we're in dx or dy. So let's do a warm-up example. It says use the region bounded by y equals x squared and y equals negative x squared, x equals 0 and x equals 1. So we're going from here to 1, and then we have our top graph and our bottom graph. So what we need to remember is that we do our top, so x squared, minus our bottom, which is negative x squared. When we put this together, we get 2x squared. Now this, of course, would be our diameter. It would be the whole thing. And we need the radius, okay? We need the radius. So remember that radius is 1/2 the diameter, which equals now just x squared. Then we can set up our volume integral, and right away it's very easy to just keep the pi out front, knowing that it's a constant. We're going from 0 to 1, and we have our radius of x squared, and we're going from the x-axis, so dx. Circular cross-sections can also be formed by revolving very thin rectangles around the axis of revolution. These circular cross-sections are more commonly called disks. A volume formed by revolving a region about a line that does not pass through the interior of the region is called a solid revolution. The line is called the axis of revolution. So right now, if we only had the one function and we were rotating it around the x-axis, that would be a solid because there's nothing to take away in between. That will make more sense when we get to the next part. So disks are solid. If a region is bounded by the axis of revolution, the volume of the solid of revolution is a sum of the volumes, essentially an infinite number of disks. Okay, so again, there's a bunch that keep going around and around and around. So to get the disk formula, it's just pretty much our volume formula for the circle. Okay, and as you can see here, we can get every step away a bunch of disks, and we then add them all together to get the volume. So we're going to set up some of these. Set up the integral for the volume of the solid formed by revolving the region bounded by x squared from y is 0 and x equals 1. So we're in dx's, okay, and of course y equals 0 or x equals 0, and then the upper boundary is at 1. So our volume would equal the integral from 0 to 1 we can stick our pi out front, and then it is our r squared. In this case, that x squared is that radius. You guys see that? Because if we actually rotated it, we would be finding the volume of this whole thing. So x squared is actually the radius. So radius squared, and we're in dx's. Okay, because we are rotating it around the x-axis. Okay. Example 2. This time we're actually going to find the volume. We're just not going to set it up. Okay, guys? So 2 steps to this. Find the volume of the solid formed by revolving the region in quadrant 1 bounded by y equals x squared, x equals 0, and y equals 4. Okay, so first what we want to do is make sure y equals 4 is up here. Okay, so we're bounded up here. So where would our function meet y equals 4? Well, it would meet it at 2, because 2 squared is 4. And then we are bounded by x equals 0, right? So we have this shape here. We are revolving it around the y-axis, so make sure that we're in dy's. And think of it as we're rotating it around. So that would make our full figure, our full solid, all the way up there. So our radius is just going to be that x squared, okay, because we would double it to get the diameter. So right now we have the volume equals pi integral. Now we're in y's. So remember, our y's go from 0 to 4. The radius is x squared dy. I made a mistake, and this is very common. What is my issue right here? Oh, wait, I want to be in dy's, but what do we have? We have x's. So what do I have to do? I actually have to solve for y. So that's the square root of y. It is usually plus or minus, but considering that we are only having 1/2, we only have to worry about the positive. Now, I could cut this mistake out from this video, but I think it's a common mistake that we have to point out. So really, our integral is pi from the boundaries of 0 to 4, square root of y squared dy. You see the difference of why this one's correct? We're in y's now. Now we can take our integral. So I have pi out front. Now, squaring of a square root is just y. So if we took the integral of y, we would have y squared over 2. And we're going the boundary of 0 to 4. When I plug 4 in, I would have 4 squared is 16. 16 divided by 2 is 8. So we'd have 8 pi minus, if I put 0 in, I get 0. So our volume is 8 pi. Very good. Okay, take a moment, change your page. All right, when a region is revolved about a line which is not one of its boundaries, its volumes is formed by a sum of volumes of washers. So it's not a solid figure anymore, okay, because it has holes in it. If you want to picture this, after the revolution, if you look on the side of it, it's going to look like a donut because there's a hole in the middle. Also, if you ever built a table or anything, sometimes you put what's called washers in between the screws to make sure there's space, and the washers have holes in it. So that's where the name comes from. So the formula for the washer, because we have to account for the hole, we have our big radius or outer radius minus our smaller radius. Okay. So example 3, it says set up the integrals of volumes of the solids formed by revolving the region bounded by y equals negative x squared plus x equal and y equals 0. So I want you guys to notice that the boundary of y equals 0 is the x-axis, and our graph is on that. So actually for this one, we don't have to do washers, we do discs because it's a solid. There's no hole in it whatsoever. So when we think of this, we have to remember that this graph is the radius, okay? So our r does equal negative x squared plus x. We also then need to find our boundaries. Using this graph, this is nice because we have from 0 to 1. But if you had to, all you would have to do is set this equal to 0 and solve. So our volume for A is pi, the integral from 0 to 1 of negative x squared plus x squared dx, because we're revolving around the x-axis. And we're done. Now B, we're going to revolve it around y equals negative 1. So imagine when we revolve around this horizontal line here, we have this huge hole in the middle. Okay, so this little r is going to form that hole. Now, the other thing we have to do here is this is our area under our curve, but we're adding this whole set right here. This whole value is the value of 1. So our big R equals negative x squared plus x plus 1. So it is our function, area under the curve, and this area here that we're setting up of 1, this value of 1. The smaller r is just that value of 1. So now we can set up our integral. Volume is pi, integral from 0 to 1. Now remember, for our washer, it is our big R squared minus our small r squared. And we are still in dx. Okay, in this case, we're going about y equals 2. So we're above the x-axis. So actually, we have here is our big R is going to be all of this. So as you can see, guys, our big R is going to be 2, because that is the full rotation. That's the outside rotation, I should say. And then your little r, Well, our little r is actually going to be this space. So this is the big R. This is the little r, right? Because that's our whole. Remember, the little r is our whole. So we have to keep in mind that the little r is going to be 2 minus our function under our area under the function. You guys see that? To get this piece, we take our whole minus a small part. So it's going to be 2 minus, I don't think I'm going to be able to fit this, negative x squared plus x. All right, so you could, if you want, distribute that negative out, so you get 2 plus x squared minus x. That makes it a little bit easier. And now when we create the volume, we have volume equals pi integral 0 to 1. And then remember, it's your big R squared minus our little r squared. And that is dx. Okay, I know this is going to be a little bit complicated to see, but let's just take our time with it. All right, example 4. We're setting these up again. So in this example, though, we're revolving the region bounded by y equals x squared and y equals x plus 2 about the x-axis. So imagine we are turning this whole thing around. Okay, so we have a bunch of washers that we need to sum up. So first thing you would need to do is find the boundaries. Now, of course, this is a graph, so it's nice that we have our x values from -1 to 2. Again, if we had to do this algebraically, we would just set them equal to each other and solve. Now, let's talk about our big R and our small r. Our big R, if you remember, is the radius from the top all the way to what we're revolving to. We're revolving around x-axis, so our big R is all of that. Okay, so our big R is going to be the area under our linear equation because that's on top. Our little r, our whole, is down here. And our little r includes the area under the x squared. Okay, so this area minus this area. So now we can set up our equation. We get v equals pi, the limit from -1 to 2. And remember, it is big R squared minus little r squared. And this is in dx. Now we're going to revolve it about the line y is 4. So we're revolving it on this horizontal line. Okay. We still have the same limit because we're dealing with x's. So from -1 to 2. Now let's talk about our big R and our little r. So now we're rotating it around here. Okay, so if you think of rotating it, what's the function that's actually on top? Well, in this case now, the function on top which is the big R, right? Our big R is going to be our x squared. And then our little r, our inner piece where that hole is going to be the linear equation. Now, the other thing about the little r, though, is because the area under the linear is actually down here, right? But we need in here. So we have to say 4 minus the area under the line would equal r. Let me repeat that. The little r is not the area under the linear, okay? We have to go 4 minus the linear to get that little r. So 4 minus x plus 2. Of course, that you could change, you can distribute, combine like terms. We end up with negative x plus 2. Now when we write this volume, we get pi, boundary of -1 to 2, big R squared minus little r squared dx. Sorry guys, I didn't realize I was writing and didn't show you. Okay. Again, this is going to take a little bit more time and more practice, so make sure we have that. What we always recommend you guys to do is try to sketch out your representation so you can see which way the rotation is and where your big R is compared to your little r. This will help you remember what to subtract or add from. And that concludes our lesson for today. I would start practicing, ask questions where you need it.